Okay, with a one-tailed test or a directional test, the hypotheses specify whether there's an increase or a decrease. We're no longer using the word affected. They make a statement about the direction. Can I contrast that with the previous couple problems? In the problem about the professors grading a different number of hours, look what it says. A different number. That's not an increase. It's not a decrease. It's just being vague about what the effect could be. It could be either an increase or a decrease. It's not committing to it. It just says different. On the problem prior to that, it said that dexterity training affects dexterity. Wow, that's not committing to a direction. It's not suggesting an improvement or a worsening. So in that case, those are hallmarks of two-tailed hypotheses tests. What we'll talk about now is a one-tailed hypothesis where they actually make a commitment. So let's get back to this red shirt business. In this case, for the general population of male customers, the distribution of tips is normal with a mean of 15.8%, a standard deviation of 2.4. For this example, the effect is that the color red will increase tips. And that's the important thing. I'm phrasing it differently now. And so we'll see how that turns out. Now, here's the blunt rendering of the hypotheses. The null hypothesis says that the tips are not increased. Notice it doesn't say affected now. It just says they're not increased. Where the alternate, the research hypothesis, is that they will be increased. And this is kind of what the researcher is frankly hoping for. Okay, well, fair enough. Now, here's the way they'd be expressed numerically. What I usually do in a case like this is, of course, read the language of the problem, right? And I express the alternative hypothesis first, which I have been calling the alternate or the research hypothesis. It's easy to do it this way. I'm saying, in my perspective as the researcher, that I'm going to increase or improve on the 15.8. So I'll say that that mean of the tips percentages with red shirts is greater than 15.8. With the red shirt, the average tip is going to be greater than 15.8. I just have to read the crux of the problem and start off with this. Then all I have to do with the null hypothesis is the opposite. Is say, okay, what's the opposite of greater than? Well, it's actually, we're going to express it as less than or equal to. To be complete, we include the less than or equal to. But in this case, with the red shirt, the average tip is not greater than 15.8, allowing us to include the hypothetical exact value of 15.8. So in this case, take it easy on yourself. Start off with the alternate hypothesis first. What is the crux of the problem? What's the gist of it? Well, that tipping is going to be increased. By wearing the red shirts, they're going to make more money. In that case, let me start off with that as the research hypothesis, the alternative, and just express the opposite with the null so it's not vexing. But you can tell right away, any one-tailed hypothesis won't have the equals and not equals. It'll actually have directions. That's what they call a hallmark or an indicator or a sign that this is a one-tailed hypothesis. We'll have the opposite direction here shortly. So notice that a directional one-tailed test requires two changes in this procedure. The first is incorporated into the statement of the hypotheses. I have to do this here. The second, the critical region is located all in one tail, not spread out over the two. Which tail is that? I'm just going to follow this arrow. If I'm predicting an increase, an improvement, something along those lines, follow that arrow. This arrow that I'm circling suggests that the critical value will be on the right. Let this be easy. Let this be as direct as it's supposed to be. This part's not supposed to be complicated. If I know the crux of the problem, I can express the alternative hypothesis. If I know that, I know the arrow goes right for an increase, and therefore I'm going to plant the tail all in one side. In this particular problem, the critical value, the Z critical value, will be different for a one-tailed test versus a two-tailed. In this case, you might remember our old friend 1.96 plus and minus. Remember old 1.96, one of our friends? In this case, it's going to be 1.65. It comes in toward the center a little bit. And why is that? Well, I look up at the Z critical values, and sure enough, 1.65 has as close as we're going to get to 0500 in one tail. And by the way, I should have mentioned that the alpha level is going to be 0.5 here. Does it say that somewhere? It actually doesn't. That's annoying. But we're going to have to remember that. The alpha level is 0.5 here. But if I assume that it was, in this case, remember, 0.500 is 5% as a decimal, right? And therefore, I'm going to use 1.65 here. Now, here's something that's an annoying coincidence. It just so happens that 1.64 and 1.65 have a tail value that's equidistant from from 0500. The tail value for 1.64 is 0505. This is 0495. And wouldn't you know it, it's an exact tie, which is irritating as heck. But we just, your textbook has used 1.65 in these examples, so I'm just producing that. Actually, in the past, I've used 1.64. But I want you to appreciate where that came from. Now, there's nothing magic about this. There are really only 2 alpha levels that we're going to use, and we'll only use 1 and 2 tailed. So it's not like you got to look up the Z tables constantly if you don't want to. It's kind of memorizable, really. But if you had to look up the Z values, sure enough, 0500, it's pretty close here. And that's what I would use for my Z critical value, because the entire 5% is going in one tail. And how do we know it's the right? Well, because we established in our alternative hypothesis that we're making an improvement. So that's the genesis of that. We'll come back to and complete this problem in the next clip.